Next up, as you can see, it's Vincent Berg with fun and games with SSL traffic analysis. So a big round of applause for Vincent.
Okay, thank you. Can everyone hear me? Okay, great. So I'm Vincent. I work for IOActive, and I came all the way here from Holland, which was a horrible flight, by the way. They didn't give me an exit seat, so fuck Malaysia Airlines. And I'm going to talk a little bit about SSL traffic analysis here. So a little bit of the outline. So what is traffic analysis? Why SSL traffic analysis? HTTP, SSL-specific traffic analysis. Some examples, a little bit about the library I wrote. I'm going to put all that code online later, and then having some fun with Google Maps. So basically, what is traffic analysis, right? So actually, it's really, well, this is it. It's deducing information from patterns in communication. It's the Wikipedia definition. So you don't look at the contents of whatever is floating by. You just look at like timing information, all that stuff. So we use traffic data. So identities, call signs of communicating parties. So when you look at network traffic, you look at MAC addresses, IP addresses, but that's it. You don't look at the contents of the packets. Time, duration, length of communication, maybe location of sender and receiver, but not the content. That's traffic analysis. And there's this guy at Microsoft Research, George Denises. He did a lot of really cool stuff on traffic analysis. He did a lot of traffic analysis on Tor, all stuff. So I strongly recommend, if you want to learn more about the stuff, to go there. I mean, I'm not going to tell you guys like really new stuff about traffic analysis, but more of what I saw in discussions with customers is that people tend to not, especially if they're not technically minded, they tend to not understand traffic analysis. So I started messing around and wanted to create a little bit of an example that pretty much everyone can understand. So, and I'll work towards my talk towards that. So some examples of traffic analysis, well, not in the networking or hacker realm. So first of all, we had Operation Quicksilver. So this was in the Second World War, and where the Brits, they fed the German intelligence true and false information. They supplied really small units, army units, with a lot of radios, and they created a lot of fake chatter on all these radios with call signs and all that on troop deployments. And based on that, German intelligence assumed that the invasion in France was going to happen at Pas-de-Calais and not in Normandy. So another really cool example was the timing analysis. I'm sure most of you guys have heard about it. This was 2001 already. Timing analysis on SSH keystrokes, reducing the entropy needed to brute force a password, all that stuff. And one of the coolest ones, this is a relatively recent example, is the one on Skype. So 6 months ago, this paper came out, so phonotactic reconstruction of encrypted VoIP conversations hooked on phonics. And basically what they were able to do without breaking like the Skype encryption, because Skype uses a variable bitrate encoding, depending on the actual sounds that are being transmitted, more or less data is being sent. And so they were able to build up this whole model. So by doing segmentation, they started with packet lengths and then phone me segments and then do all this classification on the language and all that. And at the end, they were able to reconstruct speech, which of course is really cool, right? So this was for standardized American English. I think they were, in the paper they mentioned that they were able to reconstruct like 80% of the speech. So this is a really cool example of what you can do with traffic analysis. And this is another example. This is in my home country. At the moment we've got, well, last summer, we had this guy who drives around on the highways and he shoots at random cars for some reason. And they still haven't caught him, right? But the idea is that suppose this guy always carries the same cell phone with him, and you know the times and locations of all these highway shootings. You might be able to catch him just by looking at taking all the data retention data that like the telcos have to store, and then find maybe one phone number which was at all these places at all those times, and maybe possibly catch that guy. Also a little bit traffic analysis. So why then SSL traffic analysis? Well, SSL has been around a long time, and we've had tons and tons of problems, right? Recently, we've seen all the attacks on certificate authorities, the SSL renegotiation attacks, implementation errors. I mean, if you want to maintain your sanity, don't look at the OpenSSL implementation. usage of insecure ciphers, the Apple iOS bug of August 2011, where they didn't validate certificate change correctly, and the whole Did You Know That disaster. So why would we even bother with all this stuff? Well, there are really smart people, some of the people might be here in the room, trying to fix all this stuff, right? So at some point, people maybe like Moxie Marlinspike, who tries to replace certificate authorities with his convergence.io project, or Dan Kaminsky, who tries to solve it by getting DNSSEC adopted, and many others. And at some point, the industry will hopefully get it right. And SSL is here to stay. SSL is not going anywhere. So given that at some point all these problems will be solved, what can we then still do, right? Well, assuming that SSL is here to stay, all those problems will be solved eventually. The only recourse an attacker then has is to look for patterns in the encrypted SSL stream. You can't do much else, right? And I'm ignoring all the underlying protocol stuff, just the SSL stream. What can you then still learn from doing traffic analysis? So how would you start doing that? So, well, we've got a protocol which runs over SSL, and you start by identifying messaging patterns. And you first look at, well, is it a synchronous protocol? Is it asynchronous? Is it like request, reply? Which is easy to identify, right? You first see data from a client to a server, you see data going back, and even though it's encrypted, but you know this is the request, this is the reply. That's useful information. Asynchronous protocols make it a little bit more difficult. So mostly then you have to move on to timing stuff, identifying message sizes, all that stuff. But this is sort of how you start by trying to make a profile on doing traffic analysis of a specific protocol. So how would you apply that to HTTPS? So, well, you first start by getting all these specs out, and you read the protocol, and then I'm just taking out a few examples about HTTP, and probably most people here have a little bit of an idea how HTTP works. So one thing you notice is that, well, we know about HTTP keep alive, right? So in the old situation, you would have one connection being opened, a request being sent, a reply getting back, connection being closed. So each separate connection that an attacker sniffs on the network is one request reply. And with the HTTP keep alive, it changes. There you've got request, reply, all on the same connection. But you can still identify this, right? It's just a change in direction of data. So another one is HTTP pipelining, which is also in the specs, and pretty much, as far as I know, no major browsers support this by default, which is a good thing because it would make our life way more difficult. On the left, we've got the normal situation with the HTTP keep alive. On the right, we've got pipelining. So suppose this data is encrypted. How are we able to identify if it's just one big request the client sends or three separate ones? It's all encrypted. We can't do anything with it, right? So, and some other stuff you have to look out for when you are doing HTTPS traffic analysis. Well, first of all, the request sizes, obviously they depend on URL length, on user agent headers. User agent headers can get altered by browser plugins, all the stuff. On cookie length, which can be variable depending on the service you're using. On other HTTP headers inserted by browser plugins, intermediate proxies, and of course by actual content being submitted to the server. And HTTP response sizes mostly depend directly on request sizes, in most cases. So if you then start looking and you fire up your Wireshark and you look at like an SSL session or an HTTPS session, you will see something like this. In the beginning, you will see this, the certificate exchange, and then later on, which is highlighted there, the 1703.01.00, that's like the actual SSL record, which denotes encrypted data. So that's the only thing we're going to look at. You don't care about anything else. We're doing traffic analysis. We don't care about certificate. We don't want to do man-in-the-middle attacks. We only want to look at the structure of encrypted data and see what we can then figure out. So here you can see another screenshot of Wireshark. You can see at the top, you see client hello, server hello, key, certificate exchange, all that stuff. And then at some point, it will start exchanging application data. Right? And that's the stuff that we're interested in. So basically, you just have to parse the SSL structures and get all the lengths of all the application data that's being exchanged. That's the data we want. That's the data that we're going to work with. So I built this. It's a really simple, small library called Libtrafficker. And It's a wrapper around libpcap and libnids. Libnids is used to do like TCP IP stream reassembly. The interface is sort of similar to libpcap, so it will just look for streams. If it detects an SSL stream, it will try to parse all the records, and only if it sees application data frames, it will like give back these so-called bursts to the calling application. Right? That's a parsed SSL application data frame. And if the burst join is set, they will be buffered until a communication direction switch occurs. So this is useful if you've got a synchronous protocol, because then you're only interested in how much data the client has sent in all these different frames together until the direction switch occurs. So that's sort of the basis on what I'm working with. So how would you then apply this? So this is sort of the standard way in how a browser fetches an HTML page from a server, parses the data, and then finds like references in that HTML, for example, images. And I can create a profile of a specific website or whatever based on the sizes of the actual data that's being exchanged. So, for example, the index.html can be 1,000 bytes long, and image1.gif can be 6K, image2.gif can be 7K. And just by analyzing the encrypted data, going back and forth, I can sort of figure out, okay, well, the user is probably looking at that web page because I've built a profile for that specific web page. So this is sort of the idea. So if you then start looking at some of the literature available, there's this great paper with a little bit of a cheesy title, like Side Channel Leaks in Web Applications, a Reality Today, a Challenge Tomorrow. So Microsoft Research. And in that paper, they had this table, and this table, they basically identified for 5 big websites the actual differences in like actual objects on that website. And you see a really big difference, right? So in the standard deviation and the average object size on all these specific websites. So it's really easy to identify what website someone is looking at and do profiling and all that stuff. So this is useful. Some other cool things that were in this paper were with auto-suggest drop-downs. So we had, everyone knows Google auto-suggest. And in that paper, they describe an online health application, which was Google Health, actually. Basically, a doctor or a nurse or whatever can type in a disease, and you will get like a drop-down, and it will auto-fill it in. But it's really easy to reconstruct all this data, right? As you can see there in the image, this is an example. A user types in a list, and first it types in an L, and a request will be sent, 8 to 1 bytes. And it will get back a bunch of responses, and then LI, and then the response list will change. So but if you build up this profile, you can perfectly reconstruct what someone is typing in and what someone is doing. This is really interesting. One problem here with the whole paper is that they also did all this stuff on Wi-Fi networks. And what I didn't get was, how do you figure out which packets actually belong to a connection? So if you can sniff on like the network layer, you can see IP addresses and all that, and you can see, well, that IP address belongs to that website, which is really awesome. But if you've only got MAC layer information and the rest is encrypted and you can't decrypt the Wi-Fi, what can you then still do? Because you will just see something like this. You've got the timeline, and you've got the size of the package. How do you figure out which package belongs to which connection? There are probably like all kinds of statistical tricks to do this, but I'm not really sure. They really don't explain this in the paper, and I think it's way more difficult to do this. I've got the idea that they did it in more of a laboratory session, where they only where the only data going over that Wi-Fi connection was like the actual data being exchanged by the browser with that specific dropdown. So if anyone here has got suggestions, feel free to walk up to me later. I'd really like to know how to extract this data from when I'm just having this, like time-based packet sizes. And another really interesting one was the online invest application. So what they did there, they were able to reconstruct pie charts. So there was this online invest application which you could use to manage your stocks. And they worked with a few assumptions here. They basically said, well, okay, we assume the user has 3 different types of stocks. And for the course of a week, the user doesn't sell or buy any new stock. But we still want to figure out what kind of stocks he's got, right? So, and this external web service was running over SSL, and it would return like an image. And they were able to sniff the connection, and what they would then do is like, okay, we think that the image is like 10K big. So then they would generate like all the possible images of all the possible combinations of 3 types of stocks for that specific exchange. And the first day you would get like 800 charge, right? The second day you would do it again, but because the stock market fluctuates, like the pie chart will differ, right? So you will do it again, but you match it with all the pie charts created in the first day. And you reduce it to 80 charge, and then the day after that, 8 charge. And the 4th or 5th day, you will have like a perfect reconstruction of the pie chart, and you know what kind of stock is actually in that user's portfolio. So this was really awesome. When I read this, I was like, wow, you can do that with traffic analysis? Cool. So, and then I started looking at, okay, what can I do? I needed something of a cool example, which maybe sort of worked to show maybe to customers, to explain people what traffic analysis is. So I decided, well, why not look at Google Maps? And I had no idea if this was possible. I just started messing around with it, right? So everyone knows Google Maps. This is what it looks like. And you first start by, if you want to do this, you get this web service, and my target here is Google Maps, and you start by, well, analyzing the whole application. How does it work? How is it structured? So first you will look at Google Maps, and you'll see, well, okay, it uses this coordinate system, right? It uses X, Y, Z triplets. The X and Y, well, pretty obvious. The Z is the zoom level. And then for each specific X, Y, Z triplet, there's like one image. It's just a PNG, 256 by 256 pixels, which is being downloaded from the Google services. So, okay, we know that. So, well, we can figure out maybe something about the sizes of those images, right? Maybe we can do some profiling on that. So then you look a little bit more into the whole Google Maps traffic, right? And then you see, you will get something like this, and you see all these weird URLs, and at the top there you will see like transparent PNGs, and below there you will see some satellite imagery. Okay, so that's cool. You look at it a little bit more, and then you will see something like this. So Google Maps uses these overlay tiles. So these are transparent PNGs, and these just contain like all the city names, all that stuff, right? So in this case, you've got XYZ, the triplets, 257, 169.9, and the URL there. That's the URL that's being requested. And if this goes over SSL, you can't really figure out which actual images it is. And this is the satellite tile, the corresponding one. And you can see there again, same XYZ triplet, and the URL, this is how it works. So I started messing around with that, and so that means that every image in your browser for Google Maps in the satellite view corresponds to 2 different HTTP GET requests. And this is what's then being rendered in your browser. And I want to reconstruct it. I want to figure out, okay, what's someone looking at Google Maps? So I came up with this approach, right? So I'll just scrape all these satellite tiles. You will piss off Google if you do this. You will get banned. So I got like 4 gig of like satellite tiles. I was like, okay, this is enough to work with. It's fine. You can't really scrape everything. You would need petabytes of storage, so I wouldn't recommend doing it. But it's enough to play around with this stuff. So you scrape all these tiles, all these images, and then you create a database. And for the record, I only scrape the satellite tiles, not the overlay tiles. And then you create this database, and you map all these image sizes to XYZ triplets, right? And then there's one problem. How do you differentiate between the satellite tile requests and the overlay tile requests? Because you're just sniffing a connection, and it's all encrypted, and you need to differentiate between that, so you can only take the responses that you're interested in, namely the responses of the satellite tiles, because that's what I've created the database for. So I still had no idea if I could even do this. But my idea was then, okay, I'll see all these image sizes, and I will map those back to XYZ triplets. And then I'll try to map all those triplets back to coordinates. So, well, let's see. So then you start looking. Oh, wait. So I created this tool, gmaps-trafficker. And there's this Python tool called gmap-catcher, which is like an offline map viewer, and it also supports Bing Maps and OpenStreetMap and all that stuff. And for the record, there's nothing particular about Google Maps you should be able to use the same approach on Bing Maps or all the other tile-based mapping web services out there. And then I use this tool to generate some profile data, and then I run my tool, right? And the tool is then trying to figure out, okay, what the user is looking at. So if you then start looking at how to differentiate between the two types of requests, you will see that the mt.google.com, that's the one where the overlay images are being requested from. And the khm.google.com is for the satellite imagery. But as you can see, it's the same IP addresses, so that's difficult. How am I going to identify between the two types of requests? So I just generated a lot of data over Google Maps, and I created this histogram. And then you will see something like this, right? So you just watch the traffic, and you'll see a bunch of weird outliers to the left and to the right. That's like this weird funky JavaScript. You don't really care about that, but you will see two huge bumps. Those two huge bumps, of course, correspond to the requests corresponding to all the images, because that's mostly what you're doing when you're interacting with Google Maps. You download images. You zoom in, you zoom out, new images get downloaded. You scroll a little bit, new images get downloaded. And each time, two images, right? The overlay image and the lower-laying satellite imagery. And it turned out that like the first bump is the overlay image. And the second bump is the satellite image. So this is awesome. Now I've got a histogram. I can dynamically figure out what type of request it is, and then only take into account the specific response corresponding to the satellite imagery. So then I also created a histogram of like the response sizes. We get something like this, right? So the cutoff point is at 2K and at like 20K or so. And you'll see this huge spike in the beginning. So this is for all the satellite imagery. So the chances of encountering an image which is sort of like 2K big are way higher than something of 20K, which is obvious when you think about it, because there's so much just like blue imagery, right? It's just oceans, and all these images are sort of the same size. It's just blue. They're all like 2K, whatever. And at the complete end, there you will have the images with the most information, maybe like a mountain range hitting, hitting a forest or desert or whatever. So those images convey more information and will make it easier to figure out what a user is looking at. So I started messing around with this. And this is sort of an example, right? So you get an image size of like 12K, and I look up in my database, okay, how many images have I scraped that were around 12K? Because I take into account a little bit, SSL does a little bit of padding, so I take this range and I will end up with a bunch of coordinates. These are all the XYZ triplets, like 1 to 3, 81, 3, 12, and I do that for the next image and so on and so on. The thing is, the list of coordinates will get large ridiculously fast. So how am I going to reduce this? I need a way to actually bring this together a little bit faster. So to something which might work. So I decided to plot it. So this is for one specific zoom level, and I plotted everything, and you will see all these weird outliers, and these are all matches for images in my profile data. But then you will see at like, 65, 45, you will see something resembling a rectangle, right? So if you zoom in on Google Maps, you will have this rectangle of, 4 by 4, depending on your browser size, or 8 by 8, whatever, and all these images will get loaded like really fast after each other. So that rectangle, that in this case, is probably like the best match for the data that the user is looking at. So I figured out this algorithm, and it's not that interesting, but basically I figured out how to detect these rectangles in my data, in all the coordinates that I was seeing. And then I was trying to base my, and then I'm saying, well, okay, this is probably the best fitting rectangle, so it's probably these coordinates that a user is looking at. So I created this little tool, and I'm not brave enough to do a live demo, so I made a movie. So let's see. I see this. Okay. So on the left, you will see a browser screen. It's actually running over SSL. I didn't cheat there. I cheated a little bit. I made it like a really big browser window, as you can see. So my tool works better. Because you will get so much false positives. This is not something you will never ever be able to make a tool which will like completely correctly always identify what someone is looking at Google Maps. There's just way too much information, way too much false positives. But it sort of gives you the idea. So I created a database, and the database I scraped the area around Paris, the area around Berlin, Amsterdam, Brussels, and Geneva. Right, and you can see in the table there, those are the latitude, longitude coordinates. And in the other terminal, you will see that's my tool running. So now in the browser, I will type in like Paris, France. Yeah. Hope it works. There you go, and the tool goes, and it parses all the data, and it sees all the bursts, and it's like, what is this? I can't figure it out. Oh, well, let's zoom in one more time. Let's see. There we go. Still not there. Ah, wait. Identified 4889 to 3. Ah, Paris. Great. So it has correctly matched the traffic with the profile data for Paris. Now I'm going on to Berlin. Doing the same there. Log in. Zoom in a little bit. And there you go, 5213.26. So that's correctly identified the two cities, so I was able to do traffic analysis on Google Maps. So there we are again. So how could you possibly improve this? Well, we could scrape the overlay images, reduce the number of matching coordinates. We can only add the coordinates when the overlay images and the satellite imagery matches. We can detect zooms better. I mean, if I'm seeing a full rectangle being downloaded, or just like 4 images, if it's just 4 images, it will probably be a scroll action, like to the north, to the west, to the south, whatever. That's how we can improve this. But this is basically what I did, right? So now I'm using this movie and my tool to explain to customers, okay, well, this is what traffic analysis is, and everyone understands it, right? Yeah, it goes over SSL. Everyone knows that when there's HTTPS and there's this little lock in your browser, it's completely secure. No one can figure out what you're doing. Depending on the circumstances, you can. That's kind of what I tried to show here. And that's already it. Thank you. So, a little bit fast. Any questions?
Hello. What are some situations where, like, you can get information about the traffic volume, but you can't actually see the contents? Like, where would this be useful?
I'm sorry, I don't get your question.
Like, what are some practical applications where you can see the traffic volume, but you wouldn't be able to see the actual traffic contents?
Well, I'm not able to see the contents, right?
I know, but I'm just saying in reality, like, in what kind of situation would you want to do this?
Okay, the idea is that, so data is encrypted, but you are able to, you can still profile a specific website or a specific application that a user is using, right? So you can build up this profile data, and then just, if you're not able to break the crypto, but you're still able to monitor a user, you can still figure out what the user is doing. So that if you can't figure out, if you don't have any idea what kind of application, if it's a web application or something else, what the user is using, yeah, then you're screwed. Then you can't really do anything with it, or it makes it really hard.
Thanks.
Eddie, okay, we've got one. Okay, we've got one here, and then there's any other people? One there? I'll come back to you.
Actually, I just wanted to say there's a countermeasure called homomorphic encryption that can hide your queries. So, especially for those health privacy applications, that's probably a useful thing for people to think of doing.
I don't see how that would help against traffic analysis, But
No, just because different queries all look the same.
okay, but what does that have to do with homomorphic encryption?
All you'll see is the volume. You won't see anything else.
Yeah, but the return data will still be different, right? And it doesn't matter what kind of encryption you use. If the browser sends back an image of 20K and it's encrypted, you'll see 20K of encrypted bytes, or 10K if it's like an image of 10K. So you can still see the response sizes. I don't see how homomorphic encryption would solve that.
Well, that's because it actually batches the different bits and sends one giant request. Anyway, if you're interested, I can talk to you.
Yeah, I'd like to know a
Okay.
little bit more about it. Thanks.
Okay, I think I saw a hand right at the back there.
You said you had some uncertainty. You had some uncertainty in precise sizes.
Sorry, I can.
There's some uncertainty in precise sizes of queries because of things like user agent strings and cookie data and those sort of things. Can you use those outliers, those specific JavaScript files, to figure out the size of the user agent string and the cookie string and those sort of things to get a more accurate measure?
Depending on the circumstances, you might be able to do that. I haven't looked at that. The thing is, it's always, if you don't have to predict that data, it's always easier to, if you can just create a histogram, you don't have to, like for every user, if you're like a Google user and you've got like a Gmail account, the cookie size will be completely different, right? So for one user, your request size will be 720 bytes, for the other user, 1040 bytes. So it's really difficult to figure out in advance what the request size is going to be. So if you can do it by like the histogram I showed you, then you can basically do it dynamically, right? And figure out, okay, this is that type of request, this is that type of request. So that's easier.
Okay, we've got last two questions. There's one here.
Hey, so is there additional padding that can be added to each request to minimize the exact file you're getting, because you're going to get more correlation between...
Well, padding can make it way more difficult. For example, with the drop-down issue, that one is really easily solvable. So you just pad everything to like 2K, right? In the case of, for example, Google Maps, it's really difficult. They're not going to like pad everything to like 40K, because it will mean like 30K extra for each response. So it's kind of like a trade-off there. How much security do you want? How difficult is it to actually do the traffic analysis? But in most cases, correct usage of padding will solve your problems, but it's really hard to get it right.
Yeah. So does SSL do any padding? Or
it kind of depends on the actual negotiation that goes place. It does some padding by default, so that's why I'm not... So if I'm seeing like 20K in an encrypted response, I'm looking in my database for everything between 90K and 21K, and all those coordinates I will use, because it uses some padding, but it's not enough, like as I said.
All right, thanks.
Okay.
All right, last question.
Does compression make traffic analysis easier in any way? So, for example, help you find content by seeing...
I'm sorry.
Sorry, does compression help with the traffic analysis? So, for example, a compressed response...
well, yeah, it will help. It will help. It won't solve everything, of course, but it completely depends on the circumstances. Yeah.
All right, look, thank you guys. Can I get everyone to give him a
Thank you.
good round of applause?